So you're taking an electron beam, you're focusing it, using the focusing lens to get a very precision piece in your weld. We get into X-ray a little bit, we talk a little bit more about these things as well. But basically you're creating the beam. But what I want you to really focus on is you see how, and by the time we use these focusing lenses, otherwise this could go this way. We need to kind of converge itself to where it's focusing. You can also tell if your weld, say your weld material is a straight edge at this point, you're not going to get through the whole entire thing. You have to watch your width to depth ratios at this point, because these are straight walls and this is a tapered wall, right? So it's really important to think in any welding process, what can this do for us? Now you can pull these focusing lenses out a little bit and let that kind of spread out some to get a little bit more of a width, but you may not get as much of an intensity as far as heat there either, okay? Here's a typical fixture. Here's a good example of a weld. And when we get into discontinuities section of this book, you're going to see this exact same weld almost, but then right next to it you're going to see one to where the beam was off a half a degree, and sure enough, like right here was a section that was missing a little bit, okay? There was a void, still two straight lines in there as well. But you can also see in here the granular effect. This is more of a star pattern circular, and then this is more of a layered situation. So your grain structure does kind of change a little bit in here, and some of that's just the way things happen, okay? Read through these on your own. Resistance welding, one of three. A few things I want to talk about in here. There's several different types, which we're going to talk about the three main ones, right? This is your typical spot welding, resistance welding, which you can see on most sheet metal joining things together. Two pieces come together with electricity, a positive and a ground. They come together with a piece of metal between them. You can start it and initiate it for a few seconds. They melt together. Then you pull it out and you can do another one as well, okay? So for example, when we are measuring this, we measure by the smallest size of the weld always. So in this case, it produces a weld nugget. Here's your two shoes, it puts them together, you measure from thickness, but a lot of times it's not off the thickness, it's actually off the size of the nugget. So in this case, if we were looking at the top and it created an oval nugget, this would be our shortest diameter, this would be the size of our weld, not our long piece, okay? But as you can see, what it's done is it's heated down in to create these two concerns. Two big things here. These pieces get hot, and a lot of times we start to see craters where we've actually reduced the thickness of this weld. Sometimes it really doesn't matter. Sometimes it does, okay? All right, there's three different types. So there's resistance spot weld, okay? Pulse weld and resistance seam weld, okay? Sorry, not pulse weld, projection weld. I've never seen a projection weld, I've only ever seen a spotter seam, so I apologize. Projection weld, okay? So spot weld advantages, fast. Uh-oh. You can read through here. Semi-automatic or automatic. Sorry, I dropped the clicker, and now I'm missing the battery. Alright, moving along. Good for thin materials, there's no flex required. However, some of these situations, depending on the material, do require a water jacket. And every once in a while, you'll have to stop and clean these from time to time as well, okay? Limitations, it's primarily a shop process, so forth. Discontinuities, non-fusion areas, cracks. I talked a little bit about the craters in there as well. Burnt edges, okay? Seam weld would be the same thing, but instead of just creating a spot, you would be running two rollers up and down. You'd take two rollers like this, you got two materials, and you'd be running them up and down like that and creating this heat. So kind of like now they do it with friction stir welding, but say we were to build this big tank of fuel, right? So say for a rocket ship, now they use friction stir welding to come in and weld these two pieces of this big sheet metal they took like this, folded it together, and then they weld at the top. Okay, same thing as seam pipe or anything else. It's usually not drawn over mandrel in one piece. It's a piece of plate that they run through a set of rollers and they get it into a round shape. Okay, then they weld the top in a flash pattern or something else. Well, in a seam weld, what they can do is take this seam and they can run two parallel rollers just like this up and down that, and it creates that friction between them and bonds those two together in that butt joint. All right. Our discontinuities, so that was a seam weld versus a spot weld. Brazing. The biggest thing with brazing versus soldering, okay? Well, brazing versus welding versus soldering. Base metal is not melted in brazing or in soldering. So what's number one, what's the melting point of steel? 2,780 generally, okay? Depending on carbon content and chemical makeup, but that's what we consider 2780, 2800. So brazing's below that, welding is above that naturally, okay? Brazing filler metals melt above 840 degrees. Soldering is anything below 840 degrees, okay? Remember that number, 840 is an important number. They both require capillary action, large surface area, very small clearance, clearing surfaces, so forth. So here's a good example of what I mean by large surface. Brazing is very strong, okay, and soldering is very strong. The way it gets its strength is from sheer amount of surface area. If we were to weld this piece right here, we would typically only give it a fillet weld, right? And then the rest would be an open cavity, okay? We'd fillet weld it all the way around here, but it's a strong weld. Very high tensile strength. Brazing has a lower tensile strength, but still around 45, 50,000. But here's the deal. We heat it up, it uses the flux, and we put our heat over here, and we draw that in off of capillary action. Capillary action is literally, I want you to look the definition up, but it's drawing that in and creating that heat gap to draw that material in. Some of it's done by flux, and most soldering is done by flux. Brazing can be done by flux too, but it still requires the heat to be in the right position, okay? If all I ever do is heat this up, I'm usually just getting my brazing rod right in here. I'm not drawing it all the way in. I want to get this hot, bring my heat back here, and draw that material into my hottest point, okay? But if you notice, we have a sheer amount of surface area around that entire 2-inch surface. It's a lot of veined surface. Veined surfaces are two surfaces that are side by side. I want you to look that definition up here as well, okay? Multiple ways can be done. So for example, in this situation, this is typically what you would see as far as a torch brazing. You would use your torch to draw that in. Maybe in a situation like this, or a jig or a fixture, this might be a bushing inside of something that's already been machined. This could be done in a furnace situation, okay? You can have wire strip, foil, you can have pre-built castings that they've made sure it draws it in the same pattern, so forth. So here it gives you some brazing filler metals, all right? Okay, the different brazing methods are exactly what? They're named after their heating method. Number one, we talked about the torch. Next one could be a furnace. The other one could be induction or resistance, so heating pieces up and getting it to drawing that way. Or you could even dip them as well, depending on the situation. Okay? Strong joints, they joint to similar metals, metals to non-metals, joints to unweldable metals. You can do, I haven't looked into the ceramics yet, but I think you can braze some ceramics to some steels. I do know that like you can join with brazing, you can join brass, zinc, tin, and a lot of those things are brass actually. But you can join brass, you can join bronze, you can actually take like a stainless piece of material, like if you don't have anything to weld it up, or you don't have a TIG torch, you can braze it together with some brazing brass rod, right? And that will bond to the stainless steel material. And that's what I mean by joining to similar metals at or below that melting point. So you don't want to blow a hole in the middle of a stainless steel pipe, but you need to fix a leak or something on it. You can put a saddle around it or a piece of steel, get it fixed up until you can contain the leak and replace that piece of material. I can't tell you, being an ex-HVAC tech and plumber, I brazed and soldered a lot of pipe and a lot of material. I've also welded a lot of radiators and fixed simple things, heat exchangers, stuff like that in large buildings that most people couldn't do or they were scared to do, and so forth. I have saved companies a lot of money by being able to braze. It's a very important skill to have. And a lot of downtime too. So for example, we had an old 1980s plow truck at the last place in the mine that I worked at. And this 1980s truck, it didn't get run a lot. It only went up and down a 3-mile stretch of highway, especially when it was nasty out a couple times a week for 4 months out of the year, right? But it had a PTO that went through the center of the radiator. And that PTO that went through the center of the radiator was actually the one that helped control the hydraulic pump for the plow and everything else. So this was, it was a radiator with a hole in it. It was a custom one. It's not like you run down to Napa and buy one of these, okay? So when it popped a hole in it, they told us it would be 6 months. This was December. This was the beginning of winter time. So they were saying you could be out of a truck for 6 months. It's got a hole in it, and it's a $10,000 radiator to have a new one built. And so they come to me and they said, hey, can you do this? And I'll give it a try. At this point, it can't get any worse, And I just took my time, slowly and diligently. Number one, made sure to clean this thing out, wash it out the right way, get some gas in there, get it all flushed out, do the right procedure, and then just start slowly stacking some brass in there. And I put some copper plates in there, pinched some stuff together, opened some stuff up. I thought about the process of where it was flowing, what I could control, what I couldn't control, and so forth. And it worked great. Next thing you know, we had by the end of the night, we had our plow truck back up. It took me one shift, about 10 hours, but 10 hours of paying me $25 to $30 an hour was much better than 6 months of downtime and 10 grand, okay? So, that being said, most industry partners, I say, can you teach somebody how to braze? It's like, when we need it, and it creates a huge issue, right? But it does have some discontinuities. Read through these as you go. Cutting processes. Mechanical cutting, we're not going to talk about. You know most of that at this point. Plasma arc cutting, you know that. Oxy-fuel, we've discussed that quite a bit too. I'm going to touch up on oxy-fuel is basically here, right? Real quick, run through it. Curve for the drag. Typically, you want to make sure that you're straight up and down the best you can to get a quality cut. Multiple different gases that you can use. Different torques. It can be mechanized, it can be automatic, different setups. This is a good cut. You want to look for typically a nice square edge instead of a rolled rounded edge because it was too hot. Nice good straight cuts as well. You start getting into a tapered position where you're taking your cut like this. These lines start to turn this way. They can also come down here and start to preheat and kind of dip in and gouge and run down that back plate. You want to make sure you're using that at a straight 90-degree angle for a good quality cut. Advantages: simple equipment, very portable, cuts thinner, thick materials. However, typically it is consistent. It has to be a ferrous material and have iron in it, right? You're not going to be able to cut stainless steel on this. Even though stainless steel has iron in it, it's not a high amount of iron, enough of iron to use it as an accelerator in this position, okay? You can melt aluminum with it all day long, but it's not quite as well. It just kind of, you don't do it with any precision, I should say, okay? Does have a ton of fire potentials and hazards. Again, high chrome steels can be difficult to cut. However, you want to be able to put you can put a piece of iron on top of it, right? If you put a piece of iron on top of it, it starts the acceleration of the oxidization, and that carbon will help push right through on that stainless plate as well, okay? Air carbon arc gouging. This is the loudest one, nastiest one. It can be very effective, very efficient. Most of you have done this at this point with me as well. Naturally, you have your electrode torch, you have compressed air, you have your different types of material that you're using it for, copper-coated electrodes. They're carbon. Basically, it's reversal welding, right? We heat up this liquid puddle, and then the air blows it away. Instead of depositing it, we're removing it. Great precision, great accuracy. This is one of the handiest things in the world you could ever see. However, it's loud, dirty, and nasty. The equipment, basically, you just need a carbon arc. You need air, and you need a welding machine, just like SMAW, okay? That's it. Read through these last sections, read through some of these definitions, okay? I want to make sure that you understand the definitions of alloy, ampere, arc blow, arc length, brazing, capillary action, carbon steel, carburizing, coalescence, DCEN, EP, discontinuity, electrode, feigned surface, ferrous, filler metal, flux, inclusion, incomplete fusion, incomplete joint penetration, inert gas curve, keyhole welding, non-ferrous and ferrous steel. What are the difference between the two? What is KSI? Look that up. We'll discuss that a little bit at a later point too. Orifice, plasma, porosity, progression, slag, soldering, spatter, undercut, and waster plate. Okay, waster plate is the plate that I was talking about. Carbon steel plate you put on top. You can help accelerate the deoxidization, so forth. That is chapter 3. Hopefully I'll get chapter 4 out here shortly. And thank you and have a nice day. Come see me if you have any questions after this.